Hello, welcome to Module 3 of the course on application of spectroscopic methods in molecular structure determination. In this particular module, we will consider the concept of chemical shift, the concept of spin-spin coupling, and look at the parameters that affect the chemical shift and the coupling constant which is arising out of the spin-spin coupling. Now in the last lecture, we ended the lecture with the presentation of the spectrum of ethyl alcohol, and we indicated that ethyl alcohol has three different types of hydrogen corresponding to the OH hydrogen, the CH2 hydrogen and the CH3 hydrogen, which appear at the different frequencies in the NMR spectrum. We also discussed the possibility of having fine structures like this in a high resolution spectrum of the NMR of ethyl alcohol. Now, if the concept of chemical shift were to be introduced, one has to understand that based on this particular equation, one would expect all the hydrogens to come at the same resonance frequency, because for a hydrogen atom, gamma is constant and B0, which is the applied magnetic field for a given field strength, it would be a constant value. However, we seldom observe the same frequency for all the different types of hydrogens present in a molecule. So there must be a reason that the different hydrogens show different frequency in the NMR spectrum, which makes the NMR a very valuable tool for structural elucidation considerations. Now, when we talk about this equation, we are considering a bare hydrogen without consideration of any electron density around the hydrogen. We seldom have hydrogen without any electron density in a molecule. In fact, we will have different electron density depending upon the chemical nature of the hydrogen. If the hydrogen is highly acidic, it will be surrounded by less electron density. If the hydrogen is highly basic, it will be surrounded by high electron density. This is based on our chemical knowledge. We can say that the different hydrogens come under the different electron crowd depending upon the chemical environment of the hydrogen that is being present. Now, nucleus is surrounded by electrons, and electrons are charged particles, and they also spin in the induced magnetic field. Due to the spinning electron, it shields the nucleus from the external magnetic field. In other words, a spinning electron produces its own induced magnetic field, and this induced magnetic field is supposed to be opposing the external magnetic field. In other words, it will be shielding the hydrogen from an external magnetic field. This is called diamagnetic shielding because we are talking about diamagnetic material in most of the organic chemistry that we deal with. So the nucleus actually does not feel the applied magnetic field. It feels less magnetic field than the applied magnetic field to an extent of B0 1 minus sigma, where sigma is the shielding constant. In fact, sigma is proportional to the applied magnetic field. So B0 minus B0 sigma is the correct expression for the effective magnetic field that is felt by the nucleus. Now, sigma is a characteristic feature of the chemical environment of the proton. It depends on the electron density around the particular hydrogen that we are referring to, and hence sigma will be different for different types of hydrogens. Once you define the basic NMR equation in this particular format, incorporating the shielding constant also, then we are able to recognize why different hydrogens come in different frequencies in the NMR experiment. Since sigma is going to be different for chemically different protons, the resonance frequencies of the chemically different hydrogens will also be different. Hence, the concept of chemical shift comes into picture. Now, the definition of chemical shift can be followed in the next couple of slides. For example, if one were to refer the proton frequency in the NMR experiment as 392.432, some such large number and a fractional number, it will be extremely inconvenient to remember. Instead of doing that, instead of dealing with the actual frequencies of the resonances, one can take a reference compound, and with respect to the reference compound, one can calibrate all the frequencies, and in order to make the frequencies independent of the spectrometer frequency, one can normalize it with respect to the spectrometer frequency. And this is precisely what is done when you are defining the chemical shift values of the NMR spectrum. Now, the delta, which is the chemical shift, expressed in Hertz, is simply the difference between the sample frequency and the reference frequency, and this will be highly dependent on the NMR spectrometer. The reason this is dependent on the NMR spectrometer is that it is not normalized with respect to the spectrometer frequency. We already know that the sample frequency and the reference frequencies are dependent on the NMR spectrometer. In other words, it is dependent on the B0 that is being applied. Different spectrometers will have different B0s, and that is the reason the delta expressed in Hertz as a unit, in other words in frequency units, when it is expressed, it is dependent on the spectrometer frequency. However, if you divide the difference between the sample frequency and the reference frequency by a spectrometer frequency, then it becomes independent, dimensionless feature of the delta comes into picture. Now, the spectrometer frequency is generally of the order of megahertz, that is 10 to the power 6 hertz is what we are talking about. On the other hand, the difference between the sample and the reference frequencies are of the order of hertz. So there is a factor of 10 to the power 6 comes into picture in this particular equation, and that is why delta is represented in parts per million in the NMR experiments. The delta expressed in parts per million now is a dimensionless quantity, and it is independent of the spectrometer frequency. So it doesn't matter whether one is recording the NMR spectrum in a 60 MHz NMR spectrometer or a 600 MHz NMR spectrometer. When delta is expressed in parts per million, it is independent of the spectrometer. So whatever is being measured in one spectrometer can be easily compared with what is measured in another spectrometer. Now, the reference that is normally used for proton NMR spectroscopy is tetramethylsilane. This compound is used as a reference for the following convenient reasons. The chemical shift of tetramethylsilane is lower than most protons in organic molecules because silicon is more electropositive than carbon. So it is taken as 0 and it comes at the lowest delta value in the NMR spectrometer, in the NMR spectrum. All the protons in the tetramethylsilane, there are 12 protons in the tetramethylsilane and all of them are equivalent. We will come to the point of what is meant by equivalent a little later. For the time being, let us assume they are all chemically equivalent. So they give just one signal of high intensity for the 12 hydrogens in this compound. Tetramethylsilane is a liquid and it is miscible with most organic solvent. That is a very convenient feature because depending on the solvent that we use, we can always use the tetramethylsilane as the internal reference without having to worry about the solubility properties. Tetramethylsilane is also highly volatile, so one can also remove it very easily from the sample after the measurement is made. Finally, the most important of all the properties, tetramethylsilane is an inert liquid and it does not react with the sample itself, so sample can be recovered intact after the measurement of the NMR spectrum. Now let us talk about the scan widths in the in the NMR spectrum. Suppose, for example, you have 60 MHz NMR spectrometer and a 400 MHz NMR spectrometer. Normally, in the proton NMR spectrum, you scan from 0 ppm, which corresponds to the tetramethylsilane signal, to about 10 ppm. This is a normal scan width of the order of about 10 ppm is what is normally measured in the NMR spectrometer. Now, for a 60 MHz NMR spectrometer, the scan width of this 10 ppm would be 0 to 600 Hz. In other words, one has to scan 600 Hz of scan width to cover the region of 0 to 10 ppm. On the other hand, if you come to 400 MHz NMR spectrometer, in order to cover the same scan width, in other words, the 10 ppm scan width, one has to scan about 4000 Hz as a scan width in the NMR spectrum. So, what is a 2 ppm value in a 60 MHz spectrometer? This would be simply 120 Hz. Whereas the 2 ppm in a 400 MHz NMR spectrometer would be, the NMR spectrum would be about 800 Hz. So depending upon the frequency of the NMR spectrometer, the scan width also keeps increasing for the 0 to 10 ppm of the scan width of the spectrum. So this essentially explains the higher resolution capability of the high resolution capability of high frequency NMR instruments. Suppose if we consider a difference between 2 ppm and 2.1 ppm signal, let us say there is a signal at 2 ppm and another signal is 2.1 ppm. The difference in the 60 MHz NMR spectrometer is going to be smaller compared to the difference in the 400 MHz NMR spectrometer. In the 60 MHz NMR spectrometer, it is going to be roughly 6 Hz or so the difference, whereas in a 600 MHz NMR spectrometer, it is going to be something like 40 hertz or so. So such a large difference is there in the frequency difference is there in this 0.1 ppm difference in the two signals. There will be a large difference in the hertz value of the corresponding signal. Hence the high spectrometer frequency corresponds to a high resolution spectrometer. Let us now look into the factors that affect the chemical shift value. Electronegativity, inductive and resonant effects are essentially responsible for the changes in the electron density that one observes in the compounds, in the substances, and hence these are the parameters which essentially also affect the chemical shift value of a given hydrogen. Tetramethylsilane is taken as 0 ppm as a reference standard. With respect to tetramethylsilane, all the other samples or all the other compound chemical shift values are given. The chemical shift value of only the methyl hydrogens are given in this particular table. Now with respect to tetramethylsilane, methane is about 0.23 ppm. Now you can see here the variation is the halogen. You have the most electronegative fluorine here and the least electronegative iodine and methyl iodide. As you increase the electronegativity of the atom that is attached to carbon, the chemical shift value of the hydrogen which are attached to that particular carbon keeps on increasing. In other words, the electron density around the hydrogens of the methyl fluoride is much lower than the electron density around the hydrogens of the methyl iodide, because iodine has a lesser electronegativity compared to fluorine. Now the effect is also cumulative as you go with increasing number of halogen atoms, as in this particular case from methyl chloride to methylene chloride to chloroform, the chemical shift keep increasing from 3.1 to 5.3 to 7.2 ppm. If you compare different functional group, for example methyl alcohol, methyl fluoride and nitromethane, there is an effect of the corresponding electronegativity of this particular atom that is attached to the carbon that plays a role. Methanol comes at 3.4 ppm. Methyl fluoride and nitromethane, both of them come around 4.3 ppm. From this we can conclude that the electronegativity or the electron withdrawing effect, inductive effect of the fluorine is nearly same as the electron withdrawing inductive effect of the nitro group, because they come at the similar chemical shift values with respect to each other. Now the second aspect which is responsible, or the second parameter which is responsible, is the anisotropic effect. Anisotropy is the non-uniform nature of any property. The second parameter is the anisotropic effect, which is responsible for affecting the chemical shift value. Suppose you consider spherical electron density around an atom. The induced magnetic field will be uniform in space. In other words, the induced magnetic field as a property will be isotropic with respect to the spherical electron density around the atom. But we seldom have spherical electron density except in the case of s electron. The hydrogens that are attached to various carbons, for example, are unlikely to have spherical electron density. So therefore the induced magnetic field will be non-uniform in space. Hence the anisotropic effect plays a major role in defining the chemical shift value of hydrogen. Typically, for example, pi electron cloud of the aromatic or carbon-carbon bond or carbonyl bond, for example, they do not have a spherical electron density. They have very specific shapes and size, and these are the most common features in most organic molecules, and hence the electron density cloud, which is non-spherical in nature in this system, will lead to anisotropic effect, and we will discuss the anisotropic effect in the next two slides. Now let us consider a small experiment of taking a double bond, and this is the externally applied magnetic field. In other words, the plane of the ethylene molecule in this particular case is perpendicular to the externally applied magnetic field. Under these circumstances, the induced magnetic field because of the pi electron will have anisotropic effect such that the cylinder that is shown here, the area under the cylinder here for example, will be a shielding zone, whereas the area which is away from the cylinder, which is indicated in the blue here, will be de-shielding zone. In other words, the hydrogens which are occupied in this area, the red area, will be highly shielded, whereas the hydrogens which are away from the red shielded area will be highly de-shielded. So the ethylene hydrogen comes typically around 5 to 6 ppm, around 5.28 ppm is the actual chemical shift value of the hydrogens in ethylene molecule. On the other hand, if you consider acetylene molecule, it has a spherical electron density to start with. Unlike the kind of banana bent shaped pi electron density of the ethylene, the cylindrical electron density of acetylene itself causes an anisotropic effect in such a way that if this is applied magnetic field which is aligning with the axis of the acetylene molecule, then the red the red zone that is shown here is the shielding zone, and the area around it or away from it is going to be the de-shielding zone. The acetylene hydrogen itself falls along the axis or along the direction of the B0. Therefore, this will be highly shielded in comparison to, for example, the olefinic hydrogen, which is coming around 5.8 to 8 ppm, whereas the acetylene hydrogen comes around 1.8 ppm or so. In the case of aromaticity, aromatic rings, for example, you have pi electron cloud in the form of a donut shaped pi electron density is present in aromatic system. When the aromatic plane is perpendicular to the externally applied magnetic field, which is B0 here, the aromatic electrons undergo a circular motion which is called the ring current effect. As a result of the ring current effect, you have a induced magnetic field, and this induced magnetic field is what is being represented by the lines of forces which are shown by the red circles here. So you consider a donut shaped lines of forces around the periphery of the aromatic ring in such a manner that in the center of the aromatic ring the lines of forces of the induced magnetic field is opposing the external magnetic field. So this is going to be highly shielding in nature, whereas in the periphery where the hydrogens of the aromatic nucleus lies, the lines of forces of the induced magnetic field is going to be aligning with the external magnetic field. So this is going to be shielding, de-shielding in nature in terms of the nature of the lines of forces for this particular hydrogen. So this is represented by means of a cylinder representing the shielding zone in the red and the de-shielding zone in the blue. So the hydrogens of an aromatic ring always lies in the de-shielding zone of the anisotropic effect of the ring current effect of the aromatic ring. It is for this reason benzene comes around 7.28 ppm, which is a highly de-shielded hydrogen in the NMR spectrum. From 0 to 10 ppm it comes around 7.28 ppm or so. Now if there is a hydrogen which is placed right above the benzene ring, then that should be highly shielded in nature, and this hypothesis has been in fact tested. We will see some examples later. Now in the case of carbonyl compounds, the carbonyl pi electron also shows anisotropic effect. The anisotropic effect is such that you have a shielding zone which is shown by this shown by this cylinder as a red cylinder. So anything that falls in this particular region is going to be shielded, whereas the aldehyde hydrogen falls in the de-shielding zone, and that's one of the reasons why the aldehyde hydrogen is coming at a very high delta value. There are two effects. One is the electron withdrawing effect of the carbonyl functional group, which decreases the electron density around the carbon hydrogen bond, and secondly the anisotropic effect also adds to this particular effect, leading to a highly de-shielded hydrogen of the aldehydic systems. Now in all these cases one must remember that we are talking about a very specific geometry. We are talking about the plane of the benzene to be perpendicular to the B0 in order to observe this anisotropic effect. But in solution, the benzene ring is going to be randomly oriented with respect to the applied magnetic field direction. So what we are observing in solution is only an average effect of the anisotropic effect. The maximum anisotropic effect will be felt in this particular geometry. Any other geometry where the benzene is at an angle or perpendicular to the externally applied magnetic field, for example, will be averaged out in a solution phase spectrum. So what we are observing in a solution phase spectrum is only an average anisotropic effect of the various possible orientations of a molecule with respect to the externally applied magnetic field. Now remember, we said that if the hydrogens are just above the plane of the aromatic ring, that should be highly shielded. These are two beautiful examples to illustrate the point that you have a ring current effect, and the ring current effect produces an anisotropy in aromatic system, and this anisotropic effect is what is responsible for the shielding of the hydrogens which are placed above the aromatic ring and the de-shielding of the hydrogens which are on the periphery of the aromatic ring. Now this is 10-alanine. This is a bridged 10-alanine. It is a methanol 10-alanine. The compound was specifically synthesized to test the concept of aromaticity. This compound is aromatic in nature because of the planarity of this particular ring and the 10 electron system, which corresponds to the Huckel 4n plus 2 rule. Huckel's 4n plus 2 rule is obeyed. So this is an aromatic ring, and this methylene hydrogens just fall above the plane of the aromatic ring, and therefore they are appearing in the highly shielding zone of the ring current effect, anisotropic effect. So the two hydrogens which are indicated here on the bridge actually comes at a negative delta value, less than tetramethyl silane signal. It comes around minus 0.51 ppm or so, whereas the peripheral hydrogens, which are the aromatic hydrogen, typically come in the aromatic region, which is around 7.29 ppm. Even more dramatic example is this particular molecule. This is dimethyl dihydropyrene. If you look at the peripheral number of electrons that are present in this particular system, this is a 14 electron system corresponding to a 4n plus 2 Huckel system. This molecule is planar. You can visualize the molecule in this way. This is a planar molecule, and the two methyl group, one methyl group is above the plane, the other methyl group is below the plane, such that the hydrogens of the methyl group, both the methyl groups are actually lying above and below the plane of the aromatic ring. As a result of the anisotropic effect, which is a highly shielding zone above and below the plane of the aromatic ring, these hydrogens appear at minus 4.2 delta ppm. And this is the one of the lowest values that is reported for an aromatic system. And if you look at the peripheral hydrogen, they appear in the normal region of the aromaticity. Around 8 ppm or so is the chemical Schmidt value of the various hydrogen in this one. As you increase the number of pi electron, the ring current effect also increases. As a result of that, the anisotropic effect also increases. That is the reason, compared to benzene, which comes around 7.28 ppm, this is a 14 aniline system which comes around 8.4 ppm or so. This is a very interesting example of 18 aniline. There are 6 hydrogens which are in the interior of the aromatic core, and there are 12 hydrogens on the exterior of the aromatic core, for example. This is an aromatic system because it is an 18 aniline system. It is a 4n plus 2 system, and in this particular molecule, the peripheral hydrogens come at plus 9.3 ppm delta, whereas the core hydrogens, which are highly shielded, comes at minus 3.0 ppm delta value. So this is a beautiful illustration of the ring current effect and the associated anisotropic effect, and the effect of the anisotropic effect on the various types of hydrogens in an aromatic system. Now in saturated compounds also you have a sigma bond anisotropic effect. Let us take the example, the familiar examples of cyclohexane, for example. Cyclohexane has the chair type of a conformation. So if you are considering the axial and the equatorial hydrogens of the cyclohexane, this particular bond, which is away from the hydrogens which are indicated, in other words, if you consider this to be alpha, this is beta delta bond is what we are referring to. This beta delta bond has an anisotropic effect that causes de-shielding of the equatorial hydrogen in comparison to the axial hydrogen. So the axial hydrogen is more shielded compared to the equatorial hydrogen. Therefore, the axial hydrogen comes at a lower delta value always compared to the equatorial hydrogen. In the case of the 4 tertiary butyl cyclohexane itself, if you consider the axial hydrogen, this comes around 1.12 ppm, whereas the equatorial hydrogen comes around 1.62 ppm. Now, the case of 4 tertiary butyl cyclohexane is taken because there is no chair-to-chair interconversion in this system. So, one can easily define the axial and the equatorial hydrogen of this system because there is no flipping of the ring from one chair form to another chair form, because you have attached an anchoring group which is a bulky group, namely the tertiary butyl group. Now, let us consider the nitro derivative of the 4 tertiary butyl cyclohexane. This is the equatorial nitro functional group substituted. Equatorially substituted nitrocyclohexane. This is axially substituted nitrocyclohexane. Now this hydrogen is an axial hydrogen and this is an equatorial hydrogen. These two compounds are diastereoisomers. This is the trans isomer of the nitro tertiary butyl cyclohexane, whereas this is a cis isomer of the nitro tertiary butyl cyclohexane. Now you can see here the axial hydrogen comes at a lower delta value compared to the equatorial hydrogen, which is coming at a higher delta value by about 0.2 ppm or so. If you take the tertiary butyl cyclohexanol, here also the axial hydrogen comes around 3.7 ppm, whereas the equatorial comes around 0.2 ppm more than the axial hydrogen, around 3.93 ppm or so. So this kind of a difference in the axial and the equatorial hydrogen allows one to determine the stereochemistry aspects of this kind of compounds, where you have the axial and the equatorial differences and the sigma bond anisotropy that is responsible for the differences in the chemical shift values of the axial and the equatorial hydrogens. Now let us come back to the spectrum of ethyl alcohol. Ethyl alcohol shows 3 signals, 3 frequencies. That is okay because we have 3 different types of hydrogen in the molecule. But then why is that the OH hydrogen comes as a singlet, whereas the CH2 hydrogen has 4-line pattern, which is known as quartet, and the CH3 hydrogens have 3-line pattern, which is known as the triplet. In other words, the spectrum of ethyl alcohol shows multiplicity in the case of the CH2 and the CH3 signals, and what is the reason for this is what we are going to discuss in the next few minutes. Before we go into that, let me also say that the solvent has also a major role to play in terms of the chemical shift values. This is a solvent effect. The spectrum of this particular compound, which is a sugar derivative, is measured in CdCl3, in other words deuterated chloroform, or in deuterated benzene. You can see visually, you can see the difference in the spectral resolution in the benzene D6 and the CdCl3 spectrum, for example. So solvation can also affect the chemical shift values of various hydrogens. So in addition to the inductive effect, electromeric effect, and the anisotropic effect, you can also have solvent effect, which affects the chemical shift values of various hydrogens. Now coming back to the multiplicities that we saw in the case of the ethyl alcohol spectrum, let us consider an isolated hydrogen atom. If we consider an isolated hydrogen atom, it can either exist in the alpha state or in the beta state, or the minus half state or in the plus half state. The nuclear spin can exist in these two states. So therefore, when a radio frequency of an appropriate frequency is applied, when the resonance condition is met, there will be an absorption, and that absorption is shown in the form of a signal in the NMR spectrum. So what you see is just one sharp peak for the hydrogen that is present in the molecule. In the absence of any other interacting protons, there are no neighboring protons, so there is no coupling of any kind. Only a single peak for chemically equivalent hydrogens will be seen. Suppose you take benzene. There are 6 hydrogens in benzene, but all the 6 hydrogens are identical in nature in terms of their chemical environment. As a result of that, there will be only one transition that is taking place. So all the 6 hydrogens of benzene will come exactly at the same place as a single line. You take the example of methane. Again, all the 4 hydrogens or methane are identical, arranged in a tetrahedral fashion. That will also lead to only one kind of a chemical shift value. So methane will also give only one signal without any kind of a spin-spin coupling. Now there are 2 case scenarios that are presented here. The first case is there are 2 spins, but there is no interaction between these 2 spins. What is meant by interaction is the magnetic field, induced magnetic field of the first hydrogen is not felt by the second one, and vice versa. So that means these 2 spins are acting independently. Therefore, there are 2 transitions possible. The blue hydrogen that is shown here has a transition going from alpha to beta when the red is in the alpha state, for example. It's also possible that the blue hydrogen is going from alpha state to beta state when the red is in the beta state. So there are 2 possibilities, but these 2 possibilities are isoenergetic in nature. In other words, this will have the same frequency in terms of the transition, so that will appear as one signal. Similarly, for the red hydrogen also, it goes from the alpha to beta state when the blue hydrogen is in the alpha state or in the blue hydrogen is in the beta state. These 2 states are also isoenergetic in nature, so you will just see one signal for the H alpha and one signal for the H beta. Suppose if these 2 hydrogens are interacting in terms of spin-spin interaction, in other words, the induced magnetic field that is created by one hydrogen is felt by the other hydrogen, then it is possible that you have differences in the energy between the alpha and beta states. For example, the alpha alpha and the beta beta states go up in energy, the alpha beta and the beta alpha states come down in energy. making these two blue transitions unequal, and similarly the two red transitions also unequal. So what was originally an equal energy transition of the blue and equal energy transition of the red, which gave rise to only two signals. Now there are four signals possible corresponding first transition of this kind, the second transition which is this one, the third transition which is this one, and the fourth transition which is this one. So there are four lines that are possible. In other words, the HA goes to from alpha state to beta state when HB is in the alpha state. Similarly, when HA goes from alpha to beta state when HB is in the beta state. These are the two possibilities that you can have for HA. Similarly, for HB also, it can go from the alpha state to beta state when HA is in the alpha state. When HA is in the beta state also, it can go from the alpha state to beta state corresponding to two transitions. So a system, two spin system which are not interacting with each other essentially will act independently and give respective signals as a single line. When they are spin-spin coupled, or if they are interacting with respect to each other, then there will be a coupling between these two. They are mutually coupled to each other. A will be split into two lines. Similarly, B will also be split into two lines. This is because of the fact that HA influences the magnetic field strength that is perceived by HB and vice versa. And they are mutually coupled. Therefore, the gap between the two lines that you see for HA will be identical to the gap that you see for the two lines of the HB. The mid portion of the two blue lines is the chemical shift value of the hydrogen A, and the mid portion or the mid value of the two lines of the HB is corresponding to the chemical shift value of the hydrogen B. Now J is the coupling constant, which is measured by taking the difference between the two blue lines or the two red lines. In fact, it doesn't matter whether you are measuring it between the difference between the two red lines or two blue lines, because they are mutually coupled. This gap will be identical to this particular gap, and this is what is known as the coupling constant, J coupling constant. Now, having said what is responsible for the multiplicities that one observes in the case of two spin system, let us generalize it for many spin systems now. Initially, we are talking about in all these cases we are talking about the resonance of the hydrogen, which is indicated by the blue color. Suppose if there are no other coupling partners, it just appears as a singlet. If it has an adjacent coupling partner, then it would give a doublet, because hydrogen which is in the red is going to influence the magnetic field, induced magnetic field of this particular hydrogen is going to affect the blue hydrogen in terms of the magnetic field that is felt by the blue hydrogen. So it will appear as a doublet. When you have two equivalent hydrogens in the adjacent position, this will be splitting it into two and then further splitting it into two. 2 times 2 would be 4, but then the coupling constants are same. So as a result, you see a multiplicity which is a triplet multiplicity. If you have 3 hydrogens, equivalent hydrogens, then the multiplicity will be 4. The multiplicity can be easily calculated using the formula 2ni plus 1, where n is the number of equivalent hydrogens which are in the adjacent position or the coupling partner, for example, which are identical in nature in terms of their chemical environment, and I is the spin value of that particular nuclei. If you have a spin half nucleus, then it reduces down to n plus 1 value in terms of the multiplicity. So if you have 3 adjacent hydrogen, you will have 4. If you have 2 adjacent hydrogen, you will have 3. This is called a quartet, and this is called a triplet. This is called a doublet, and this is called a singlet. So you can now realize that the multiplicity actually tells you a lot about the structural fragment that is being present, and that is the reason the spin-spin coupling is an invaluable tool if you can identify it properly and correlate it to a structural feature of the molecule, and that solves the problem of the structure solving problem of this particular system. Let us take the olefinic system. The olefinic system, the first example, there is only one hydrogen, so you see only one transition. Suppose you have a trans hydrogen associated with this molecule. In other words, this is a trans isomer of a olefinic system. This trans hydrogen will couple with the HA, and HA will in turn couple with the HB, which is the blue hydrogen, So the blue will have a transition. There are two possible transitions the blue can have. Because of spin-spin coupling, it will appear as a doublet. Suppose if there are two different types of hydrogens, one is a cis hydrogen and another one is a trans hydrogen. The trans hydrogen can couple with this to make it into a doublet, and the cis hydrogen, which is geometrically different from the trans hydrogen, will also couple with this, but the coupling constant will be different. We will look into the parameter that affects the coupling constant in a minute. For the time being, assume that this coupling is different from this coupling. So originally the line is split into a two, and it is further split into, initially you have a singlet with no coupling. With only one coupling partner you have a doublet, and with two coupling partner you have a doublet of a doublet. Suppose if we have three coupling partners, that is one cis coupler and one trans coupling partner and one vicinal coupling partner, which is in this position, for example. So the trans coupling can be making can make the hydrogen into a doublet. The cis coupling can make it into a doublet of a doublet, and this vicinal coupling can make it into a doublet of a doublet of a doublet. A doublet of a doublet of a doublet should have 8 lines. So you can see here the 8 lines, which is the doublet of a doublet of a doublet. Now the parameters on which the spin-spin coupling depends on are as follows. It depends on the distance between the coupling partners and the intervening number of bonds. The more number of bonds that you have and the intervening between two atoms or the two hydrogens, smaller will be the coupling. More importantly, the dihedral angle plays a major role in the coupling partners of vicinal hydrogen. We will see the relationship in a minute. The coupling constant is largest when the dihedral angle is about 180 degree, and it is very small when the dihedral angle is about 90 degree. In freely rotating bonds like in the alkyl chain, average J values are obtained. In other words, this is an illustration that we will give at a later stage. Now this is a diagrammatic representation of Karplus equation, which is relating the J value to dihedral angle in a cos type of a relationship. What is dihedral angle? Dihedral angle is the angle which is obtained by the two hydrogens which are on adjacent hydrogen atoms. In other words, if you look at this picture, this is like an open book kind of a conformation that you have. The dihedral angle is this particular angle denoted by phi here, and between this hydrogen and this hydrogen, that is the dihedral angle. In a Newman projection, this is represented, the dihedral angle is represented like this. Now as the carbon-carbon bond rotates, the dihedral angle can vary, and depending upon the dihedral angle, average dihedral angle of that particular molecule, it can have value anywhere from 0, which is an eclipsed conformation, to 180, which is an anti-conformation of the two hydrogen. In the anti-conformation, you have the maximum J value, which is roughly about 14 hertz or so, whereas when it is at 90 degrees, for example, it has the minimum coupling constant, which is about 1 or 2 hertz or so. When it is 0 dihedral angle, this has a value of about 10 to 12 hertz or so in terms of the J value that we are talking about. This is applicable to all vicinal coupling, freely rotating vicinal coupling, as well as not freely rotating vicinal coupling. Now let us summarize what we said in the previous two slides. The spin-spin splitting pattern can be for a spin-half nuclei as follows. The number of lines that one expects is 2ni plus 1. Otherwise it is n plus 1 for a spin of half, because I is equal to half, where n is the number of equivalent protons that couple. This is extremely important. The protons have to be equivalent, then only the coupling constants will be same, so that you can interpret it with this ni plus rule, n plus 1 rule. So when you have an adjacent hydrogen, each of the HA and HB is going to be doublet with one single coupling constant of JAB. When you have two coupling partners which are chemically equivalent partners, then HA will be a triplet, because n plus 1 will be triplet for this hydrogen, and this will be a doublet because there is an adjacent hydrogen which leads to a doublet. Suppose if you have a CH2, CH2, each would be a triplet. HA will couple with HB, and in turn HB will also couple with HA. Each of them will appear as a triplet. So if you have an ethyl group, it will be CH3 will be a triplet and CH2 will be a quartet. So now you can understand why ethyl alcohol spectrum showed one triplet and one quartet, because there is a CH2 CH3 group there. In other words, looking at the spectrum, if you see a triplet and a quartet which are mutually coupled in terms of being a same J value, one can come to the conclusion that there is an ethyl group present in the system. Similarly, if you have a doublet and a septet, septet is a 7-line pattern, you come to the conclusion that there is a structural element which corresponds to an isopropyl group. Only isopropyl group will give you a doublet and a septet. Doublet for this methyl group because it is split by the CH, and septet is for this hydrogen because it is split by 6 equivalent hydrogens of the methyl group in the system. In the case of spin-half nucleus, the line intensities of multiplets can be easily calculated or predicted from Pascal triangle. The line intensities are corresponding to the coefficients of the binomial expansion. For example, if it is a doublet, it will be a 1:1 intensity ratio. If it is a triplet, it will be a 1:2:1 intensity ratio. If it is a quartet, it will be a 1:3:3:1 intensity ratio, and so on. And these are the actual multiplets seen in the actual spectrum. For example, this is a triplet, quartet, quintet, and a septet are the multiplets that are shown here. And this is the Pascal triangle, which can be easily constructed by adding two numbers and bringing out the central number by adding the adjacent numbers, for example. And you can see here, when you come to large multiplicities, the end lines are much less intense in comparison to the central lines. So it is possible to easily miss these multiplets that are seen in the septet or heptet kind of a multiplicity. So one needs to be careful in expanding or zooming the spectrum in the y-axis so that the intensities can be very clearly seen, because of the fact that the central intensity relative to the end intensities are much higher. So you may miss out the end lines all the way in the spectrum. This is a correlation chart of chemical shift of various protons in the aromatic molecule. Typically, the proton NMR spectrum is scanned between 0 to 12 ppm or so, and the most acidic hydrogen, which are the carboxylic acid hydrogens or hydrogen bonded enolic hydrogens, they come in the region between 10.5 to about 12 ppm or so. The aldehyde hydrogen typically come between 9 ppm to 10 to 10.5 ppm, sometime even all the way up to 11 ppm it can come. The aromatic hydrogens typically come in the region between 6.5 to about 8.5 ppm. The ones that are electron rich in nature, that is endowed with electron donating substituents, will have a shielding effect. So as a result of that, it will come in the region of 6.5 to 7.5, whereas those aromatics which are electron deficient or endowed with electron withdrawing functional group, like the nitro group, they will appear in the region between 7.5 to 8.5 ppm. So one can tell from the NMR chemical shift value whether the aromatic system is a electronically endowed system or electronically depleted system in terms of the electron withdrawing substituents or electron donating substituent being present, because it is reflected in the chemical shift value in this narrow region. Olefinic hydrogen typically come in the region between 5 ppm to 7 ppm. It can come all the way up to 7.5 ppm also, depending upon the electron withdrawing substituent that is attached to it. Mono-substituted derivatives, as we have seen in the earlier cases, depends on the electronegativity of the group that is being attached. That can come anywhere between 2.5 ppm to about 5 ppm or so. Di-substituted derivatives can come between 4 ppm to about 6.5 ppm or so. Hydrogens which are exchangeable hydrogens, like for example the acidic hydrogen of phenol or alcohol, they constantly undergo exchange from one molecule to another molecule. They can appear anywhere in the spectral region between 0 to 10 ppm, and usually they are broad signals which are easily recognizable in the NMR spectrum. The easiest way to identify them is to do a deuterium exchange. In other words, you take the sample and record the NMR spectrum and see if there is a broad signal corresponding to a OH of an alcohol or a phenol, and then add a drop of D2O and measure the spectrum again. This broad feature should disappear because of the exchange of the hydrogen with the deuterium. Because they are fairly acidic hydrogen, they have the capacity to exchange with the deuterium, and the signal corresponding to that particular OH peak will be disappearing in the NMR spectrum. This is called the deuterium exchange studies. This is a table correlating the structural feature to the J value or the coupling constant values. The coupling constant depends on the number of intervening bond between the two hydrogen. If it is more than 4 or 5, the coupling is close to 0, unless, for example, there are some rigid orientation ideal conditions are met by these two hydrogens to couple with each other. Otherwise, typically the vicinal couplings come in the region between 6 to 8 ppm in freely rotating system, or between 5 to 7 ppm in a more substituted bulky kind of a system like this. The vicinal coupling can be highly dihedral angle dependent if there is a restricted rotation or some rigid geometry that is present, and this is essentially governed by the Karplus equation which we saw earlier in terms of the equation as well as the diagram representing the Karplus plot. Vicinal coupling between aldehyde hydrogen and the adjacent hydrogen is generally very small. Sometimes you don't even see this coupling. And geminal coupling between two hydrogens, provided they are diastereotopic in nature, they are chemically non-equivalent as well as magnetically non-equivalent in nature. They can come fairly large values of coupling constants are reported. Between 12 to 15 ppm is the coupling value that one sees for geminal coupling of this kind. Now, in the case of olefinic system, you can have a trans coupling, or you can have a cis coupling, you can have geminal coupling, or you can have vicinal coupling of this type, where the hydrogen is in the adjacent carbon, not part of the olefinic system. Now, the trans coupling is a fairly large coupling. Typically, it comes around 16 Hz or so. The cis coupling is smaller compared to the trans one, comes around 10 Hz or so. The geminal coupling is of an sp2 carbon is really very small. Often one can miss it. For example, it is typically of the order of 0.5 to about 3 Hz or so. This kind of a vicinal coupling is of the order of 3 to 11. It depends on the dihedral angle. If it is not a freely rotating system, it will be heavily dependent on the dihedral angle. Propergely coupling of this type is very small. Typically 2 to 3 Hz is what is measured. In the case of aromatic systems, one can have orthocoupling, metacoupling as well as paracoupling. Orthocoupling is the largest coupling, typically of the order of 7 to 8 Hz is what normally one sees. Metacoupling of the order of 1 to 3 Hz is what is normally seen. One can miss the paracoupling completely in the NMR spectrum because it is a very small coupling, typically of the order of 0 to 1. So oftentimes you don't see the paracoupling at all. Let us look into some definitions in terms of chemical and magnetic equivalence. When we say two protons are chemically equivalent, that means they have identical chemical environment, which means they will have identical chemical shifts. They are called isochronous nuclei because they come in the same frequency. Typically, homotopic and anisotropic hydrogens in organic molecules are chemically equivalent. Now, if you take the example of methane, all the 4 hydrogens are arranged in a tetrahedral fashion. It is highly symmetrical. TD symmetry is what is present. So, as a result of that, the chemical environment of each of these hydrogen is identical. So, all the 4 hydrogens will appear as a singlet in the NMR spectrum of methane. In the case of ethane, as long as this carbon-carbon bond is freely rotating, which is the case normally in the case of ethane, all the 6 hydrogens will appear as a singlet only. Benzene, for example, is a D6H symmetrical molecule. You can do either the symmetry criterion or substitution criterion also. If you do a mono substitution of benzene, you will get only one isomer of nitrobenzene or one isomer of chlorobenzene, which means all the 6 hydrogens are equivalent in terms of chemical equivalence. So, in the case of benzene, all the 6 hydrogens come as a single peak in the NMR spectrum of benzene. You take a meso isomer of this kind. This is a meso isomer. It has a plane of symmetry. So, these two hydrogens are related by the plane of symmetry. That means they are anisotropic in nature, and such anisotropic hydrogens are also chemically identical in nature or chemically equivalent in nature. You take less symmetrical molecule, like for example in the case of naphthalene and in the case of, for example, anthracene and so on. In the case of naphthalene, if you take, there are 2 types of hydrogen, the HA hydrogens, which are the alpha hydrogens, and the HP hydrogens, which are the beta hydrogens. So, there are 2 sets of chemically equivalent hydrogen, namely HA and HB. Similarly, in the case of anthracene, there are 4 HA type of hydrogens, which are chemically equivalent, 4 HB type of hydrogens, which are chemically equivalent, and the hydrogen in the 9 and 10 positions are chemically equivalent, and they are chemically distinct from HA and HB very clearly. Phenanthrene, if you take, it has only one plane of symmetry. So, on either side of the plane of symmetry, the hydrogens that appear are chemically equivalent. So, there are 5 sets of chemically equivalent hydrogens in the case of phenanthrene. You take either a monosubstituted aromatic derivative or a pyridine derivative. It doesn't matter which kind of examples you take. The orthohydrogens or the 2,6 hydrogens are chemically identical. The 3,5 hydrogens are chemically equivalent, and the 4th hydrogen is chemically distinct from the 3,5 and the 2,6 hydrogens. So, HA, HB, HC are the symbols that are given for the chemically distinct hydrogens in this case. So, in order to define a chemically non-equivalent hydrogen, you give different alphabets as subscript. In order to define chemically equivalent hydrogen, you give the same alphabet as the subscript, and this is called Pople notation. Now, magnetic non-equivalence can be defined for two protons that are said to be magnetically non-equivalent if they have different magnetic environment. What is meant by different magnetic environment means you compare, let us say, a set of chemically equivalent hydrogen. You want to find out whether they are also magnetically equivalent. If there is another hydrogen in the molecule, look for the geometric relationship between the set of hydrogens which you are comparing to the hydrogen which is away from these two sets. Suppose if they have identical geometrical relationship with the other hydrogen, then these two hydrogens are said to be magnetically equivalent. If they don't have same geometrical relationship, then they are magnetically non-equivalent in nature. Typically in organic compound, diastereotopic hydrogens are non-equivalent in nature. They are both chemically as well as magnetically non-equivalent. For two protons to show a spin-spin coupling, they must be magnetically non-equivalent. Otherwise, they will not couple with each other. They may or may not be chemically non-equivalent. This is something we will define in the next slide or so. Let us take this example. There is a chiral center in this molecule. So we are talking about chemically non-equivalent protons in molecules in this particular slide. Because of the chiral center, these two hydrogens are diastereotopic in nature. Because if you substitute this hydrogen with a substituent, you will get a different isomer compared to substituting this hydrogen with another substituent, a different isomer. So they are truly diastereotopic because they are adjacent to a hydrogen. And diastereotopic hydrogens are chemically non-equivalent in nature. You take a DL isomer. Earlier we considered a meso isomer with a plane of symmetry. The DL isomer does not have a plane of symmetry. It has a C2 axis of rotation. These two hydrogens are related by C2 axis of rotation. As a result of that, they are diastereotopic in nature. This is an example of the same type like here what we had a chiral center here. This is also a chiral center. The adjacent methylene group is a diastereotopic methylene hydrogen. Now this molecule is not a chiral molecule. This center is not a chiral center, but it is a prochiral center for the reason that these two hydrogens are pro-diastereotopic in nature. Suppose if I substitute this hydrogen with a substituent, that makes this a chiral center automatically, which in turn makes this center to be a chiral center automatically. So these two hydrogens, although there is no chiral center present, they are still considered to be diastereotopic or pro-diastereotopic, for example, for the reason that it generates a chiral center by means of a substitution criterion. Now let us define what is chemically equivalent but magnetically non-equivalent. Let us say, for example, a monosubstituted derivative is what we are talking about. We want to assign whether these two hydrogens which are chemically equivalent, that is the two ortho hydrogens are chemically equivalent, whether they are also magnetically equivalent or not. In order to define the magnetic equivalence, you compare it with another magnetically active nuclei. Let us take, for example, this hydrogen as a reference hydrogen. With reference to this particular hydrogen, these two hydrogens are not geometrically related in the same way. This is ortho, whereas this is para. So they will not have the same coupling constant in terms of the magnetic environment of this hydrogen to this hydrogen, and this hydrogen to this hydrogen will not be identical. So although they are chemically equivalent, they are now magnetically non-equivalent. The same logic holds good for the HB hydrogens also. You compare it with, for example, HA hydrogen. This particular HA hydrogen you take as a reference point. This has a para relationship, whereas this has an ortho relationship. So one can define the magnetic non-equivalence and chemical equivalence in this way. Chemically equivalent hydrogens need not be magnetically equivalent, and chemically non-equivalent hydrogens are by definition magnetically non-equivalent. Now these are three isomers of difluoroethylene, for example, the geminal difluoro, the trans difluoro, and the cis difluoro. In each of these cases, these two hydrogens are chemically equivalent but magnetically non-equivalent. For the reason fluorine is F19 fluorine is a magnetically active nucleus. So that makes these two hydrogens magnetically non-equivalent because one has a trans relationship, the other one has a cis relationship. Geometrically they have two different relationships, so they cannot be existing in the same magnetic environment with respect to this fluorine here. Take this example where you have two identical substituents situated in the para position and aromatic ring. There is a plane of symmetry, the vertical plane of symmetry and a horizontal plane of symmetry that makes all these four hydrogens identical. They are chemically as well as magnetically identical. On the other hand, you remove one of the planes of symmetry along this direction by putting X and Y substituent instead of two X substituents here. Then if we consider a pair of chemically equivalent hydrogen, they are magnetically non-equivalent for the same reason that we defined in the case of the mono-substituted derivative. Now the parameters that one can obtain from the NMR are the chemical shift values of various protons, the coupling constants values of various multiplets, and the relative ratios of signal intensity or the areas under the peaks are proportional to the number of protons responsible for each signal. For example, in the case of ethyl alcohol spectrum, we saw three signals with the intensity ratio of 3:2:1. The 3:2:1 comes from the fact that you have a CH3 and a CH2 and a OH group. So then signal intensity or the area under the peaks are actually proportional to the number of protons responsible for each of the signal. Suppose if we have a mixture of compounds like orthonitrotoluene and paranitrotoluene, if you integrate the methyl signal, there will be two different methyl signals for these two compounds, ortho and para. They are distinctly different compounds, so there will be two signals. If you integrate the two signals and take the ratio, that will correspond to the mole ratio of these two compounds in this mixture. So this is very useful information because it allows you to quantify using NMR spectroscopy, using a suitable internal standard, what are the mole ratios or what is the absolute molar amount that is present in the mixture. Now in this particular presentation, so far we have seen the chemical shift, concept of chemical shift, the concept of coupling constant and the concept of J values and delta values, and the parameters that are responsible for affecting the J values and the delta values. We also defined what is a chemically equivalent hydrogen, what are chemically equivalent hydrogen, and what are magnetically equivalent or non-equivalent hydrogens. I hope you understand the concepts very clearly. Let us move on to the next lecture. Thank you.